So the next talk will be given by John Robert Brucato. The title of their talk is Water Desorption from Lunar Sample Analogues to Support the ESA Prospects Instrument Development. So John, take it away.
Yeah. Hi, everybody. So how are you? I hope you see my screen. Okay, so let me see. Move.
Yeah, we can see you, no problem.
Yeah. Okay. As you probably know, so European Space Agency is developing an instrument package that is named the Prospect. So to operate on board of LUNAR-27 lander from Roscosmos, Russia, and this lander is equipped by a driller that will be delivered and made in Italy. So, and it will be go to the depth at 1 meter, depth deep on the South Pole lunar surface, and the grains and the sample will be extracted and delivered to a oven and the mass spec that will detect the volatiles on the sample, especially concerning the presence of water. So in this respect, a team has been set up by ESA in order to investigate the properties of the lunar soil, and with respect to the desorption and diffusion of water, and in specifically in order to evaluate the capability of the driller and the system to detect the water. And so in this respect, we have investigated in the laboratory, so the water desorption from some mineral analogues and lunar simulants, in order to quantify the sublimation kinetics of the desorption. So especially we made a temperature program of desorption experiment in which we have a ultra high vacuum chamber, the pressure inside of 10 to minus 10 millibar, in which is interfaced with a cold finger. So the cryostat can get 17th Kelvin, and so the cold finger is covered by water ice that is introduced inside the chamber by this system, in which there is a pre-chamber in which we prepare the sample, and so the volatiles, and so it's condensed on the cryostat. And so the cold finger is heated at a constant rate of 1.51 Kelvin per second, and so the water is desorbed by the cold finger and detected by a quadruple mass spec. Okay, so the temperature program of desorption, TPD, is usually a measuring of the desorption of volatiles, in this respect of water, and this is an example of the TPD curve. So there is increasing the temperature of the cold finger continuously. So we have the release of the water in the gas phase, and so the mass spec is detecting. So when all the water is released, so the intensity is decreasing again. So generally the TPD is modeled by the Polanyi-Wigner equation, in which we have the desorption rate, an exponential factor, the heating rate that we use in our experiment. This is a surface coverage. In our cases, we have just used a monolayer regime, and so we have the desorption energy here. So I'm going to show the major result. So we have made the desorption just from the naked cold finger, so that is a nickel-plated copper, and after we covered the cold finger with a thin layer of those grains of the size of 5 micron grains, and the layer is almost 100 microns of different minerals, so olivine, spinel, statite, quartz, and the lunar simulant. And so we measured the TPD of these on these samples. So this is the case of the cold finger without any dust. And so we have the temperature of desorption of the water is 141 Kelvin. And so we can derive the desorption energy by the equation. And so when we use the olivine dust in this case, so we can see that we have a different shape of the desorption peak. So we have the main first order, the desorption of the water is occurring at the lower temperature, so it's 130 Kelvin. And so we have one shoulder in this case, and another it seems to be there. But in any case, we have for all the sample that we have measured in this case, so we have the main peak and the shoulder. So we interpreted that this shoulder has a diffusion of the water inside a thick layer of dust. So, and we have measured not only the desorption energy of the water, but also the diffusion parameter inside the layer. This is some example of what we have obtained in the lab. So again, the first major peak and the second shoulder. This is for the case of quartz, that is synthetic. So in this case, we have a very homogeneous sample. In the other, we have used the natural terrestrial minerals. And so this is the case of lunar simulant. And again, so we can see the major peak and this shoulder. Okay, going to the result. This is the TPD for each sample that we have used in our experiment, so we can compare the different temperature and so on. And concluding, so we have that in general, so we haven't any major changes in the desorption temperature of water from minerals that we have investigated, included the lunar simulant 2. And so we derived the energy, the desorption energy, and the diffusion parameter. So this is clearly these results are just used in order to derive these important parameter, that is desorption energy, that can be, and that is going to be used by the other team in order to evaluate the desorption of water in different conditions, because here we have used just laboratory condition in which we have a very high desorption rate, so we can model in different conditions of, for example, compared to what occurred on the moon, in which the temperature is higher of sublimation, it seems to be higher than that derived in the lab. So this is the major results, and so thank you for your attention.